Now, let's start second part of this lecture. Sometimes we apply the load, right? And that load is not always along the axis of the force of the component, right? Like this one. This is off axis. This is off axis but parallel to this axis of the shaft, right? So P equivalent opposite load are being applied, that is 150 pound. And sorry, I should switch to the presentation mode, right? So 150 pound is being applied, and if I take the section over here, right, if I take the section over here, so what will happen, right? Since it is off-centered, off-centered 5-inch, this force and this force will be causing an equivalent opposite axial force, as well as, because this is an off-centered, so it will be causing a moment of 750 pound. And this is called eccentric loading. We have already discussed in chapter 1 somewhere, right? Another type of a loading could be that is called transverse loading. Transverse loading is the loading which is applied vertically to this longitudinal axis. This is the longitudinal axis, this one, and this is the load that is being applied vertically to this longitudinal axis. So that is called the transverse load, right? It could be a concentrated load like this one, or it could be a uniformly distributed load like the one you can see in forthcoming lectures, like this one. So it is uniformly distributed across the longitudinal axis, right? So whenever we have this sort of situation, then definitely we can go for this type of loading. And if you take the cross section along this one, so there will be equal and opposite longitudinal transverse loading for the longitudinal force, that is P. This is equal and opposite. This is equal. This is equal and opposite, and besides that there will be a movement into this direction. Since this line of action of these two equal and opposite forces is counterclockwise, so this force will be in clockwise direction, right? But in this chapter we will not be considering this shearing force, because this is along the plane of this section, so this will be the shearing force. And but since we are not dealing with the shearing force in this chapter, and we are dealing with a pure bending, so we will be considering only this moment, which one, this one. And if I cause this, it will be in this direction, so they will be equal and opposite to moments are being applied into this, right? Superposition. There may be, now we have already seen that there may be multiple type of the loadings, like axial loading, there may be torsional loading, chapter 3, and there may be the bendings, which we are going to discuss in this chapter, right? So there may be multiple type of the bendings, so they will be causing multiple type of the stress. Multiple type means something will be causing normal stress, like bending will be causing normal stress, axial force will be causing normal stress, torsion torque will be creating torsional or the shear stresses, like and this V, or this particular force over here, this one, this will be causing again the shear forces and the shear stresses in the body. So law superposition says that if we want to calculate the normal stress or the shear stress, we calculate all the normal and the shear stresses accordingly, and then we sum up all these stresses, obviously shear with the shear and normal with the normal, to get the final or the complete state of stress of any body which is being subjected to the multiple loads conditions, right? So I mean, as we proceed in this course, so you will see there may be multiple type of the loading. There may be axial force, there may be torsional force, there may be some movement as well. So you will have to see that what sort of force, what sort of loading condition will be generating what sort of stresses, and then you will accordingly add all the similar type of the stresses, mean normal stresses with a normal one, and the torsional stresses or the shear stresses with the shear stresses one, and then you will add up all these stresses, and you will get with with a particular state of stress, which will be defining that if these different types of loading are being implemented on this particular component, so how much will be the normal stress there and how much will be the shear stress over there, and then we will use this information somewhere in the Mohr circle. That will be that will be in the end of this chapter. So right. So uh, whenever you have this couple moment being applied onto this one, right? This you have already, obviously this is the z direction, this is x-axis, this is y-axis, and this is z-axis. So you can see these x, y, and z here as well, right? So and if I take the section at C, so it is the section at C, and you again prismatic is member is there. So what will happen there? We have already seen that whenever we apply the bending, into this one. Whenever we apply this, now this is the Z bending, right? Z moment that is causing the bending, right? Upper part is going into the compression, lower part is going into the stretching or the tensile loading, right? So neutral axis is neutral, no force is there, no shear stress is there, right? So means the surface above the neutral axis and surface below the neutral axis, above will be under compression and lower will be under tension, right? So the sum of all because these are equal and opposite forces, so sum of all the forces will be equal to zero. Sum of all the forces will be equal to zero, but the sum of the moments will not be equals to zero. Let's go to the somewhere on the one note, so that I can explain it in a better way, right? So stop. I'll stop the video now, right? Now, for example, uh, this is the section. This is neutral axis, and this is a small dA, right? Small part, that is dA, and this is above the neutral axis, so stresses will be going in because that will be under compression, and here the stresses will be coming out because this part will be in the tensile. So this is the basically compression region, and this is basically the tensile, and this is basically the neutral axis, where you will find no force, resultingly no stress, right? So these are equal and opposite forces, right? We know sigma is df over dA. So force will be sigma dA, right? So df, for example, if this is a smaller area, so we can say this is the df, right? Sigma dA. So this is basically the force. Since they are equal and opposite, they will cancel out each other. But if there is some distance over here and distance over here, that maybe you can say pi. So this will be the moment, right? So moment will be force, this one multiplied by y. This will be the small amount of the moment that is being added on this one. Now see how the moment will be going. If this is the neutral axis, right? So if this is the neutral axis, right? So about this axis, if force will come, it will try to rotate this one into this direction, and similarly this will also try to rotate this into this direction, right? So they are both in the same direction, right? So when they are in the same direction, so moment will be added. Sum of all the forces will be equal to 0, but moments will not be equal. Sum of moments will not be equal to 0 because they are in the same direction. This will be going into this way and this will be going into this way because directions are in this way, right? So they are, since they are in the same direction, so they are being added. So this moment will be there. So you will have df over here. So you will have df here, df here, df here, df here. So all dfs will be there. Above the neutral axis, all will be under compression. Below the neutral axis, all will be in the tensile tensile loadings. So but their moment direction will be same, so they will be keep on adding with each other, and by the end of day it will cause this particular rod to be bent into this direction because this is the moment about the z-axis, right? Fine. Now I'll share the slide with you. So sum of all the forces equals to 0, fx equals to 0. So fx is sigma x dA, we have just seen, because this is now, this is the force being applied into this direction, x direction. So sigma x, this is the force, sigma is F over dA, right? And about the moment about the y-axis again 0. If this is, these are the z is the distance between this component, this dA with this one, about z-axis, about y-axis, sorry. So if you see it, this force is coming out, this force is going in, because this region is in the compression and this region is in the tensile. So about y-axis, how they will be going? This will be trying to move this into this direction, while this will be trying to move this into this direction. So they are against each other. So a moment about y will be equals to 0. But moment about z will not be equals to 0, because we have already discussed in the one note that one is going in, another one is going out about the neutral axis. So both direction will be same. When direction will be same, so they will be going to add up. So mz, moment about z is not equal to 0. That is moment about equal to z is m, and minus sign is showing that because this component is below the neutral axis, that is under the y will be, y distance will be minus, so you can take it as a minus dx, but doesn't make any difference if you take it positive, because by the end of day you will get the sign correction while calculating the stuff with it. So that is not a major chunk over here. So y is the distance, this is the distance from the z-axis. So y sigma x dA will be equals to moment of this one. So again, we have already seen this slide that if you have a transverse loading and we take the section about C axis, about the C section, so there will be two equal and opposite forces. This will be causing the shear stress forces, and resultingly these will be causing shear forces, resultingly shear stresses, and this particular movement will be causing the bending of this one. So when we will ignore these, so we will be dealing with a pure bending, that is chapter 4. And when we are considering this shear stresses, so we will be in chapter 5, where we will be dealing with this one, right? So this is again, you have the neutral axis over here. This is basically the neutral axis, and this is the y distance between the neutral axis or the origin to any certain point, and maximum displacement from this neutral axis is, this is basically the neutral axis, and this is the c is the maximum distance from the neutral axis to the uppermost surface, and y is any distance between this, any point on this surface, like this one here in this particular case, right? So in this particular case, when we deal with the bending, so lines, horizontal lines always remains parallel to each other. These are basically the horizontal lines, These are the horizontal lines. They always remains parallel to each other. Where, like you can see over here, this is the undeformed section. This is the undeformed section, and this is the deformed under the bending, similar stuff, right? These are the parallel lines. They are still parallel to each other, horizontal lines which are parallel to each other, whereas the vertical lines are non-parallel, no more, any more parallel. They are no more parallel, right? So here, this is the undeformed section, so everything is parallel, both horizontal and vertical. But when you apply the moment bending, so there is basically the horizontal lines remains parallel, but the vertical lines no more remains the parallel to each other. So they get some rotation because of this moment, and they become they become uh, not parallel to each other, right? But they remain straight. They remain, both remain straight. So when, if you look at that, this, so you will have like section like this one. So here you have reduction in length, and here you have increase in length. So we know whenever you have increase or decrease in the length, so we deal with the normal strains, because normal strain deals with the change in the length of the segment, whereas the torsional or the torque, that causes the change in the any sort of deformation, angular deformation of that particular component. So since no angular deformation is there, there is no angular deformation is there, so we are not dealing with the torsion. In this particular case of the pure bending, we will be dealing with the normal stresses and normal strains. So what is neutral axis? So we are talking about the neutral axis is the axis about which no stresses are there. It experiences no force, resultingly no stress. But how you would determine what is the basically where is the neutral axis? So if you are applying a force into this direction, so where will be the neutral axis? So there are three options: A, B, and C. So what do you think? It should either it should be A, or it should be B, or it should be C. Which one? So basically it is, in this particular case, it is A, and if the force is being applied into this direction, so it will be along this axis. So the darker one is the neutral axis. So how we define the neutral axis? We define the neutral axis that the axis about which compression and the tension take place, right? We are in this particular case, when we will apply this force, so compression will be into this one, right? So it will go into this one, into this shape, right? So so when it will go into this shape, so this axis, that is x and z axis, you will get the compression, right? You will get the compression and the tension along the x z plane. Whereas in this particular case, you will get, it will go into, if this is the one, so it will go, it will bend, like this one. Here it will bend like this one, right? And in the second case, it will be bending like this one. So the neutral axis will be lying in this format, and that is because that is the axis, that will be the, this will be the axis, this will be the axis along which compression and the tensile will be. In this particular case, it will be the axis, this will be the axis, this will be the axis about which x-axis planes are about which the stresses and the strains are being carried out. So we saw how the force is being applied on that particular component, and about which axis or about which plane, the compression and the tension is being taken place, right? So here we end our chapter, today's lecture. So in the next lecture, we will discuss more about the theoretical aspect of the centroids and rest of the stuff, and then we'll go ahead accordingly. So thank you very much. for listening, and we will share all the queries either on the emails, or we can have a interactive session on the Zoom, so that we can deal with your queries and we can discuss it accordingly. You can email me, you can WhatsApp me if you have any concept problem. So we will go for this in the interactive section, maybe tomorrow or day after tomorrow. Accordingly, we will plan, and then we will have a interactive section to deal with your queries. Thank you very much. Now, बहुत शुक्रिया.